In this lesson, you're going to learn about the characteristics of functions, and we're going to use this cube root function, f of x equals the cube root of 3x minus 4, along with its graph, to talk about these characteristics. Let's first label the graphs over here. I've put the parent graph, y equals the cube root of x, on here as well. It's the dashed line that you see here. But the graph that we're looking at specifically, f of x, is going to be this purple graph, this curve right here, and I'm just going to label this f of x. We don't want to put too much on the graph to get in the way. Now the first question is asking us to notice where the graph is increasing. So it's asking, as x values increase, where are the y values also increasing? And when you have a graph to look at, it makes it much easier. You're just looking for where the graph is going uphill or moving up. And if you look along this graph, it has to be left to right. If we look from the left to the right, we're increasing really the entire graph. At some places we're increasing at a faster rate, like as we get close to this y-axis, but we're increasing the entire graph. So in answer to question number 1, where is the function increasing? It's increasing from negative infinity to positive infinity. So it's increasing over the whole interval, the whole graph. The next question is asking, what is the y-intercept of the graph? To find the y-intercept, we're looking at the y-axis, and we're looking to see where the graph touches the y-axis. It appears to touch right here, at -4. I'm going to rewrite this number since I've written over it. Now we can confirm that algebraically. I'm going to go ahead and write what we suspect to be true here. What is the y-intercept? It's going to be 0, -4. And then to verify that, we're going to take our function up here and we're going to rewrite it and let x equal 0, because if you notice here, of course, to be a y-intercept you have to have a 0 for your x value. So let's do that. Now we have f of 0 equals the cube root of 3 times 0 minus 4, and 3 times 0 is 0, the cube root of 0 is 0, and 0 minus 4 is -4. So we were right. Our y-intercept is going to be 0, -4. The next question is asking us, does the graph have symmetry? Let's get rid of some of the lines that I've drawn on here so we can take a better look at the graph. Now that's better. So, does the graph have symmetry? Let's take a look and see if we can identify any line symmetry. If we look here at this line, if we fold the graph across that line, it is not going to match. It's not going to have that symmetry. If we fold it on the y-axis, again, it's not going to match. The top and bottom portions of this graph are not going to be on top of each other. If we try folding the graph this way, it's still not going to work. It's going to do something sort of like this, and that's not what we're looking for. And if we try it in the other direction, the same thing's going to happen. So by inspection, it doesn't appear that it has any line symmetry. We could fold it a couple of times across a couple of lines and maybe come up with something, but just one line, there's no line for this one. It does have point symmetry though, or it appears to have point symmetry. If we put a point right here at 0, -4, and we take this piece and we spin this graph 180 degrees, it's going to land right here, and this piece would land on the other side. So before reaching a full 360-degree rotation, this graph is actually going to map onto itself. So it does have point symmetry. I think we should verify that algebraically before moving on though. The way we're going to do that is we're going to take the parent graph, y equals the cube root of x, and verify that it has point symmetry, rather than trying to work with f of x. Since f of x is just a dilation of the parent graph, a dilation and a translation of the parent graph, it hasn't changed shape. It's changed size and location, but the shape is exactly the same. So if the parent graph has point symmetry, so does our new graph. Now instead of writing y equals the cube root of x, I'm going to put it over here as g of x equals the cube root of x. And then I'm going to use the fact that all odd functions have origin symmetry. Our parent graph appears to have origin symmetry. If it's an odd function, then we verified it has origin symmetry. So let's do that. We're going to evaluate for g of -x and see where that takes us. That'll give us the cubed root of -x, which results in the opposite of the cubed root of x. And now we're right back to negative g of x, which is what we were looking for. g of negative x equals negative g of x, and therefore it's an odd function. All odd functions have point symmetry or origin symmetry, and that tells us that our new graph, while it doesn't have origin symmetry, does have point symmetry. Before answering the last question, let's go ahead and clean this graph up one more time. Question 4 is asking, what is the sign of f of x when x is negative, or what is the sign of y when x is negative? So let's go to the negative part of the x-axis and take a look. Over here is where our x values are negative. We have no positive y values when our x values are negative. There's nothing happening up here in this space. Everything is below. So this question is an easy one. What is the sign of f of x when x is negative? All of our y values are down here in the third quadrant, so they're negative as well. Now you know a bit more about the characteristics of functions. See you next time.